Hello. I hope that you're having a good day. We are continuing here with hypothesis test. In particular, we're looking at a hypothesis test for mu when sigma is known. So moving from some generalities about hypothesis testing, we're going to look at a particular procedure here. The assumptions within this setting are one, that we have a random sample. Two, we have a normal population or a quote-unquote large sample. Three, that sigma is known. Now, our test statistic here is x bar minus mu naught over sigma over root n. So our test statistic, you recall, is the quantity that we get from our sample and what's stated about the null hypothesis in order to make a decision about our hypotheses there. Okay, I want you to note that I'm plugging in a mu naught value there. So let me back up a little bit. When I look at the general form for our statistic, a test statistic is a relevant statistic minus the hypothesized value divided by the standard error. Okay, well, those three things are popping up in this formula here. My statistic is x bar. My standard error of x bar is sigma over root n, and we've seen that from earlier sections. And mu naught is the null hypothesized value of mu. Okay, and so me having a subscript with a naught on it reflects, this reflects that we are assuming H naught is true. Okay. In other words, this is the value of mu under the null hypothesis. Recall, mu, the population mean, is unknown. Under the null hypothesis, we specify that it has this particular value, mu naught. That's our test statistic. This statistic is analogous to the confidence interval x bar plus or minus z sub alpha over 2 times sigma over root n. What I mean by analogous is we use, or under the situation where we used this confidence interval, we also use this test statistic. The assumptions here are the same. Okay, what is the distribution of this test statistic? Sometimes we call this the null distribution. Two things to consider here. If the underlying population is normal, then this ratio x bar minus mu naught over sigma over root n is distributed standard normal, and that's under H naught. And this follows from a theorem that we have seen before that said if the population you're sampling from is normal, then x bar is also normal. And what we've done here is we have standardized x bar, assuming the null hypothesis is true. That's what I mean when I say under H naught. And so x bar standardized under the null follows a standard normal distribution. Now, if the population is not normal but n is large, then this ratio, the same test statistic, is approximately standard normal under the null hypothesis, and this is by the central limit theorem. Okay, so the central limit theorem is driving the result or allowing me to get the null distribution of this test statistic. Okay, here's an example. So take a moment, hit the pause button, read this example. Okay, so upon reading this example, you will see that we are doing a hypothesis test, hopefully, on a population mean mu. What's going on here is there's a claim that we want to test about some parameter. All right, and if you read closely, you'll see that the parameter of interest under step 1, we're going to identify that here. The parameter of interest was a population mean mu. All right, that should be parameter. All right, here's the parameter of interest. We're asking a question: do the data provide sufficient evidence to conclude that this year's mean retail price of all history books? We're wanting to say something about that quantity there. Okay, so this parameter of interest, mu, is going to be defined as follows: the mean retail price of all history books for this year. And there's a claim that has been asked about that. The claim, or there's a question that's been asked about that. Has this mean increased from the 1997 mean, which was 4350? So that's the claim we want to test. Okay, so that claim we want to test, I'm going to put in the alternative hypothesis first. So in terms of identifying hypotheses, I like to identify the alternative hypothesis first, H1, or if you want to write HA, that's fine. We are interested in testing the claim, is mu greater than 43.50? This is the claim we want to test. Okay. We want to know if we have sufficient evidence to conclude that's true. Do we have overwhelming evidence to make that sort of statement? Recall, to go from H0 to H1, you need overwhelming evidence. Another way we phrase that is, do we have sufficient statistical evidence to make such a statement? But if H1 is that mu is bigger than 43.5, H0 is that mu is equal to or less than or equal to 43.5. Okay, that's my null hypothesis. Now, this kind of test is typically called a right-tailed test. A right-tailed test, because what we're going to see is in our rejection region we are going to deal with the right tail of a normal distribution. But it's the thing that's driving it in terms of it being a right-tailed test is this alternative. They're tied together. We have a greater than in my alternative, and that makes it a right-tailed test. Step 2 here. Step 2 is the test statistic and its distribution. So the test statistic here, let's see, my pen's not wanting, there we go. Test statistic. Okay. We only have one test statistic. This z-test statistic is x bar minus mu naught over sigma over root n. Now, in order for me to use this test statistic, I have to have the assumptions involving this test statistic satisfied. So are these assumptions satisfied here? Do I have a random sample? Do I have a normal population or a large sample? And is sigma known? Okay, so let's see here. We have a random sample. 40 randomly selected books were taken. So that's assumption is satisfied. We have a large sample size. We got 40 data points to work with. There's the 40 prices for this year's history books in that table. And then also we have assumed that the standard deviation of prices for all of this year's history books is 7.61. So we have knowledge of the standard deviation of the population. Okay. So our test statistic, Z equals, is this test statistic. And, let's see, let's make that a pin. This follows, this ratio follows an approximate standard normal distribution. And so this quantity here, the approximate standard normal distribution, that's my null distribution there. All right, this is the null distribution, or the distribution of the test statistic. Okay. All right, step 3, choosing a significance level, and then also looking at the rejection region of this sort of test. The significance level, you recall, is the chance of making a type 1 error. The significance level here has been chosen for us, and in most settings it is chosen for us. Alpha is 0.01. Was chosen there, we said, at the 1% significance level. The significance level and the direction of the alternative hypothesis drive what the rejection region looks like. So let me draw you a picture of the rejection region. Recall the rejection region is the values of our test statistic for which we reject the null hypothesis. And those values are on the null distribution. And so here's my distribution of my test statistic. It's a standard normal distribution. And because I've got what's called a right tail test, that is my alternative here again is mu is greater than 43.5, I'm going to have a right tail rejection region. And it's going to be out in the tail of the distribution. Okay, so I'm going to come out here at, in general, it's Z sub alpha for a right tail test. If we were in a left tail test situation, we would be at negative Z sub alpha. We would draw that. But Z sub alpha here is Z sub 0.01. And if you look that up in your chart without taking the time to do that, that's the 99th percentile of the standard normal, which is 2.33. Now, this Z sub alpha, again, is the value of Z such that the area under the curve to the right of that value is 0.01. This is the rejection region here. Anything to the right of 2.33. And so what this is saying is if I see a test statistic bigger than 2.33, I'm going to reject the null and accept the alternative. Now this is quite intuitive. If you look at this test statistic form here, it's x bar minus mu naught. Okay, so if I just focused on, let's just focus on x bar minus mu naught for a little bit. If x bar is bigger than mu naught, then that, in some sense, that's evidence for the alternative and against the null hypothesis. But it has to be bigger than mu naught by a certain threshold, and that threshold is identified by the rejection region is determined by the number of standard deviations x bar is greater than mu naught. Okay, and that's what this whole measure is here. It's the number of standard deviations x bar is from mu naught under the null hypothesis. Okay, so the rejection region helps us identify this sort of thing and think about for what values are we going to dismiss the null and accept the alternative. This is the rejection region. Let me partition this off here. The decision rule is just in words what the rejection region is telling us. It would say something like this: to reject H naught if Z observed, that's the observed value, the observed test statistic, if my observed test statistic exceeds Z sub alpha, which is 2.33. I'm going to reject H naught if that's the case. Otherwise, we fail to reject H naught. Okay. And failing to reject H naught is a weaker statement. It's a very weak statement of support for the null. It's very different than saying we accept the null hypothesis. It's more of an inconclusive result, if anything. That's step 3. Step 4, we are going to check our assumptions here first off. So, checking our assumptions for our test statistic, that's what we're going to do here. Okay, so what were the assumptions? We kind of already walked through this. Really, the test statistic in step 2 that we have here, really this Z test statistic, the only one we have so far for our hypothesis test, is valid. So I'll write this out. Oh, let's see. The test statistic in step 2 is valid because it satisfies the 3 conditions. In particular, I'm going to be explicit about this. We have a random sample. Number 2, or the second one here, we have a large sample. In this case, n is 40. Thirdly, sigma equals 7.61. That is known. Okay. So our assumptions to use x bar minus mu naught over sigma over root n are satisfied. Also within this step, we're going to calculate our descriptive statistics. Well, so what I need to do is I need to take here, I need to come up to my sample. I've got 40 data points. So in order to use this test statistic to compute it in this step, I need x bar. So I need to take the sample mean of these 40 data points. Mu naught, that's the value of mu under the null. Sigma, that's given to us, and n is the sample size. So what we need is x bar. I'm confident that you can take the average of those 40 data points. And if you do that, you'll see that the sample mean is 46.93. So, So what I want to state here is from the sample, we see that X bar is 46.93. N is the sample size, that's 40. And sigma, this is really given though. Sigma is 7.61. This is given. Okay, so that's what I need to compute my statistic. So the observed or the computed test statistic is as follows. It's a z-test statistic. I'm going to put a subscript for observed there, OBS, and that's going to be x bar minus mu naught over sigma over root n. Just plugging in here, I get 46.93 minus mu naught. Again, that's the value of mu under the null. What is that? So under the null hypothesis, mu is less than or equal to 43.5. So I really have a lot of different values of mu that I could choose under the null. The best strategy though is to choose the one that will yield a most powerful test, and the one that will do that is the value, choosing the value that's closest to the threshold. That is, it's the value at 43.50. I won't go into a lot of details on why we choose that, but we choose the one at 43.50 at that threshold value. And I think I may have misspoke. I said we choose the value that gives them it would give them a most powerful test, but it also protects against a type 1 error the best. Okay, so we are going to plug in here 43.90.50 rather, divided by 7.61 over root 40. Okay, and if you do that computation, you will get 2.85. So make sure you can get that. So what is this saying? This is saying basically that X bar is bigger than mu naught by 2.85 standard deviations. And that's actually a large distance. It's a pretty large distance. It is a large distance on the standard normal distribution. When you get out to z equal to 2.85, you're pretty far out in the right tail of the distribution. So, but the takeaway to formalize this in terms of making a decision and interpreting it is as follows. We're going to look at the two ways to make a decision. Recall, I'm going to do that first. Now, in general, you don't have to do both ways. I want you to be able to do both ways and understand both ways. But in order to do a hypothesis test, you really only need to do one of the approaches. So the first approach, checking to see if the test statistic lies in the rejection region, 2.85. Does that fall in the rejection region? Let's go look at our rejection region here. The rejection region was anything bigger than 2.33, and so clearly our test statistic falls in the rejection region. So because of that, because our observed test statistic, which is 2.85, falls in the rejection region, we reject H naught and accept H1. Okay, that's the decision part. It's kind of a mechanical thing. You just look to see, does the test statistic fall in the rejection region? And it does. So we reject H naught and accept H1. We have strong evidence for H1. Well, what does that mean in the context of this problem? What that means, in other words, So I'm going to put a semicolon there. In other words, we have sufficient statistical evidence to conclude that this year's average history book price is larger than the $43.50 that was the average from 1997. Okay, so we've made a decision, we've interpreted it. This is, again, this is, typically called the critical value approach. The critical value being 2.33, and we compare our test statistic to the critical value to make a decision. The other approach is the p-value approach. I want you to be mindful of it. The p-value, recall, the definition of it is the probability of seeing another statistic, in this case another z-value, as extreme or more extreme than what we saw. What did we see? We saw 2.85. Okay, so as extreme or more extreme would be greater than or equal to 2.85. Now, in general, extreme can be greater than or less than, but when we look at our alternative hypothesis, it's a right tail test, it's greater than, so we're talking about extreme away from the null and towards the alternative. That's what the p-value is after here. You can, when you have a left tail test, the notion of extreme will be less than, okay? But for us, it's greater than or equal to 2.5 in this problem. And so what you would do is you would use table, your normal distribution table, and find the cumulative probability up to 2.85, and you would get 0.9978 there, and that would be 0.0022. Okay, so if you want a picture to what I'm doing here, this over here is 2.85. The area under the curve to the right of that is 0.0022. Okay, and I get that by taking the area under the curve to the left, which is 9978, and subtracting that from 1. Now, in terms of using this to make a decision, we compare it to alpha. So 0.0022 is clearly less than 0.01. So just to be explicit, this is less than the alpha value of 0.01. Hence, in this approach, we also reject H0 and accept H1. Okay. To put a picture to what's going on with our p-value, 0.022 is the area under the curve to the right of 2.85. Recall, we had another value here, which was 2.33, and that was z sub 0.01. The area under the curve to the right of 2.33 is 0.01. And so that total area here and here combined is 0.01. And so the reason I'm drawing this picture in this way is to demonstrate that if you check to see, does the test statistic exceed their critical value? Yes, it does. And that happens if and only if the p-value is smaller than the significance level. Okay, so those two approaches are consistent. They yield the same result. Last question here on this page. If we are testing mu, then why is this test statistic not practical? Okay, so we've done all this this long problem, this procedure. Did we just do something that's not practical? Well, yes. Directly, it's not practical as we have it. You know, pedagogically, we've gone through a lot of good things that are practical, but this particular formula, as it stands, is not practical because we don't know sigma. We don't know the standard deviation of the population, and so we don't have anything to plug in there. So we need an approach that's more practical. And you're probably thinking, well, I know that approach. Yeah, let's just replace sigma with the sample standard deviation S, and we're going to do that as we move to this next section here, a hypothesis test for mu when sigma is unknown, a more practical situation test statistic. But that'll be for the next video.